Good afternoon, everyone. I welcome you all in the second session of the course on geospatial technologies for archaeological applications. The topic for today's session is ground-based optical remote sensing for archaeological studies. I am Dr. Poonam S. Tiwari, and I'll be dealing with what are the ground-based optical remote sensing technology and their application for archaeological studies. So yesterday, you have been told about how remote sensing can be used for archaeological studies. And you have seen that the optical as well as microwave hyperspectral remote sensing can be used for identification of sites, archaeological sites. They're mapping the landscape of the archaeological area. Also, they are used for exploring the new sites which would be useful for archaeological exploration. The remote sensing technology is also used for making buffer zones so as to protect the heritage area. Now, once these archaeological sites are identified and they are means known to us, the heritage that we discuss, we have some built monuments also, and we have some certain artifacts, built monuments in these archaeological areas. And our technology, the ground-based technology, would be mainly focusing on how to create a 3D model of these monuments of archaeological importance. Also, how to know what was there previously, doing the damage assessment of the monuments of the heritage monuments, how we can automatically do the damage detection, how we can create the digital documentation of these archaeological monuments. Now, as you already know, that for any building, for any monument, for any building, we require a 3D AutoCAD drawing. So for these monuments, we don't have such type of drawings available with us, because these monuments were built long ago. We don't have these drawings. So now, if we create very high quality 3D models of external as well as interior of the monument, we can create the 3D digital blueprint of these monuments. And these 3D digital blueprints of the monuments can be used for restoration purpose of these monuments if there is some calamity, or if they require certain restoration. So that would be the topic for tomorrow's class. Today we will be seeing what are the techniques of ground-based remote sensing which can be used for archaeological applications. And in this technology, in this session, we will be talking about the 3D mapping techniques, ground-based 3D mapping techniques. Now, because as I have already told you, that our basic idea is to generate 3D models, dense 3D models of these monuments. And for generating the 3D monument, 3D models, we will be utilizing certain techniques, and one by one we will be discussing these techniques and how these techniques can be used for heritage documentation. So first of all, you must have heard about the photogrammetry technique. So this photogrammetry is an image-based technique in which the images are captured from multiple angles, from various directions. The images are captured and the dense or sparse 3D point cloud is generated. The photogrammetry, when we are using the camera on the ground, we call it as terrestrial photogrammetry. So I will be explaining the procedure of terrestrial photogrammetry, as well as how this technology is being used for creating 3D models of the monuments. So this terrestrial photogrammetry is quite cheap, but it requires the expertise of the operator is required. Now, the next technique is range-based techniques. Now, in this range-based technique, as you must be aware that we have these laser scanners. So laser scanners can be used, and these laser scanners, they generate very dense 3D point cloud. They are very fast, very easy to use, but naturally the instrument of the laser is quite expensive. Some of the instruments are bulky also, but there are fewer models that are now available in the market, which are not so bulky and they are handy also. To generate the 3D point cloud or 3D database, we can also use surveying methods, which are classical surveying methods such as total station, GPS. But these surveying methods, they are only able to give us very sparse point cloud. And these sparse points will have very low density, very low resolution, and they are quite time consuming also. So we will be focusing on the first two methods, that is image-based method, that is terrestrial photogrammetry, and range-based method, that is laser scanning. So one by one, we will be looking at this technology, what is the basic concept of this technology, and how this technique can be used for 3D documentation of cultural heritage sites. Now, going into a little bit more detail about the range-based 3D modeling and image-based 3D modeling, what are the benefits and what are the disadvantages of these technologies. So in the range-based 3D modeling, that is terrestrial laser scanner, we are able to get very high vertical accuracy. That means height or depth accuracy is very high. These are very easy to use. You can only set up the instrument and it does the scanning of the entire area itself. There are certain scanners which provide us the full waveform data also. Instead of discrete points, it gives us full waveform data also. And this full waveform samples the return signal very rapidly and stores the entire backscattered energy of the emitted pulse. So in this full waveform data, apart from range, so apart from depth, we are able to get other physical properties such as the width, the amplitude of the returning wave, and these properties can be used to identify the material also. Okay, so this was about the range-based 3D modeling. The terrestrial photogrammetry, in terrestrial photogrammetry, we can have instantaneous or rapid image acquisition. If you have a camera, you can use that camera and capture the photographs then and there. Now, what we have observed and we have experimented also here at IIRS is that any type of camera can be used for terrestrial photogrammetric applications. Even the mobile phone cameras can be used. After a certain procedure is followed, you can use even your mobile phone cameras. So, and that procedure is also very simple. That procedure would be the calibration of your camera. So after calibration of the camera, any type of camera can be used for photogrammetric application, for terrestrial photogrammetry. Now, because the camera is with you, so the cost of acquisition, processing and analysis is very less compared to the other technique, compared to the range-based technique. It is also, the terrestrial photogrammetry is also providing high accuracy, and it is very portable and flexible because you can use any camera, you can take it anywhere. Whereas in case of laser scanners, the instrument sometimes is bulky. You have to set up that instrument and take the 3D model. One by one, we will be looking into these techniques. So starting with terrestrial photogrammetry. Now, photogrammetry, as we understand, is the science of quantitative analysis of measurements from the photographs. So making precise three-dimensional measurements from the photographs is the technique of photogrammetry. Now, photographs are two-dimensional. From this two-dimensional photograph, how we can derive the third dimension also. And this third dimension is the depth in case of terrestrial photogrammetry. In case of aerial and satellite photogrammetry, it becomes as height also. Okay, so how we are able to do this is very simple. We are observing this photogrammetric visualization in our day-to-day life. We all are having, all are able to visualize which object is closer to us and which object is far away from us. And this we are able to do because we are having two eyes, and these two eyes are situated at two different positions. So the photograph, the image is captured from first eye, image is captured from second eye of the same object. In the brain, the stereographic processing is carried out, and we are able to generate the 3D model of the area. Similarly, for photogrammetry, what we do is we capture the photograph of that object from multiple positions, multiple view angles. We are capturing the photograph of the object, and then we perform certain operations by which we recreate the same condition as it existed at the time of photography. That means we are recreating the conditions, at what distance the two photographs were captured, what was the orientation of photograph 1, what was the orientation of photograph 2, and so on. Like this, certain mathematical equations have to be solved, but the computer does it, the software does it itself. So this is how we are able to generate 3D models. And once we have the 3D model, we can make precise measurement over this 3D model. This 3D model, using certain ground control points, we can correlate its coordinates to the ground coordinates also. And once we have done that, we can make the precise measurements on this 3D model. So based on where the camera has been placed, the photogrammetry can be of three different types. That is aerial, satellite, and terrestrial photogrammetry. In aerial and satellite photogrammetry, the distance between the object and the camera is quite high. That is why these are also called as far-range photogrammetry. The terrestrial photogrammetry is also termed as close-range photogrammetry because the distance between the camera and the object is less. So this is the basic principle of photogrammetry. As you can already see, the object is captured from two different positions. The same object is captured from position A, OA, and position OB. From OA, image A is created. From the position OB, the image B is created. When we recreate the same, using these photographs, when we recreate the same conditions as it existed at the time of photography, that means when we find out the camera position and the camera orientation at the time of photography, then we are able to generate a 3D model of the object. The entire procedure or the processing of in which we calculate the camera position and camera orientation is called as orientation of the photograph. So in the orientation of the photographs, the location of each camera's perspective center means the position of camera at time of photography, and the rotation of camera about its axis are generated. And once that is done, by using image matching, we can generate the dense point cloud. We will be not going into the details of photogrammetry here. If you wish to understand in depth about the photogrammetry, you can go to our other lectures on 3D modeling. So that has complete details about terrestrial photogrammetry and even aerial and satellite photogrammetry. In the previous lectures, in the previous courses, we have discussed it in detail. Here in this course, we will be dealing only with the application of the technology in the area of archaeological excavation and monitoring and studies. Okay, so now terrestrial photogrammetry has been used extensively for archaeological studies. So I'm here showing you a few examples where around the world, the terrestrial photogrammetry was used for creating 3D models of important archaeological artifacts and monuments. So this slide explains the 3D model generation of Beyond Buddha Tower in Angkor Wat in Cambodia. As you can see here, the multiple photographs, to be precise, 16 number of photographs were captured from all around the Buddha Tower. As you can see, the position of the cameras is listed out here, position 1, 2, 3, 4. You must be seeing that in all the position of the cameras are placed in such a way so that the optical axis of the camera is oriented towards the center of the monument or center of the object. So this is required when we are doing terrestrial photogrammetry, when we are taking multiple photographs. So we should take the photographs in such a manner so that the optical axis is converging. So that is why terrestrial photogrammetry is sometimes known as multi-station convergent photography. Okay, I will again repeat it. Multi-station convergent photography. Multi-station because you can capture the photograph from multiple stations, from multiple positions. As here in this particular slide, they have taken the photograph from 16 different positions, and it is convergent photography. Convergent in the sense that all the optical axis should be converging at the center of the object. So once this is done, you can do the orientation of these photographs. Now I have shown you the photographs also. You can see this is the photograph for the Buddha Tower. This is the photograph and the 3D model has been generated. Just one second. This is the 3D model for Buddha Tower of Cambodia. Okay, you can display it in real color. You can give the color from the photographs also, or what you can do is in form of color ramp also you can display it. Now, once you have created this 3D model, I will show you in the studies that were done in IIRS that how these 3D models can be used for various other applications. This creation of 3D model is one thing. Using this 3D model, you can do a proper documentation of this monument. You can do damage detection of the monument. If there are certain cracks, there are missing portions, you can do a damage detection. There are other applications also, which I will be discussing by the end of this lecture. Okay. So another example of utilization of terrestrial photogrammetry for creation of 3D model of archaeological sites. This is Beit Gorgeous Church. This church, as you can see here, it is in a gorge. That is why the name has been given here. Okay. Just one second. Okay, it is in Ethiopia. Then here again we have shown you the position of camera at the time of photography, position of camera. So you can see so many photographs were captured all along the church. Okay, and this 3D model was generated. This is another church done by University of Hanover. This is a Byzantine church. These are all of archaeological importance. Okay, so you can see here the camera has been placed here and it is being captured. The photographs are captured and ultimately the dense 3D model is generated. Okay, I think all of you must be knowing about this Bamiyan Buddhas. Bamiyan Buddhas were very tall Buddha statues made carved out of stone in Afghanistan. The militants, the Talibanis, they put bombs here and exploded and they destroyed these Bamiyan Buddhas. So this was a UNESCO World Heritage Site, and what later on after the destruction, what after that only people realized that we should try to protect our archaeological heritage, and first of all we should first of all do the documentation, absolute documentation of our monuments. And suppose there is because of some earthquake, because of some calamity, war, some monument gets destructed, then something can be done for restoration of these monuments also. So using the this was a big project at that time, using the using the pieces of the Bamiyan Buddha, the terrestrial photogrammetry was carried out and virtually they were reconstructed. The Bamiyan Buddha statues were reconstructed, but virtually. So this is the area of Bamiyan Buddha. There were two statues. One was a larger one called as Great Buddha, and one was smaller one which was called as Small Buddha. So both Great Buddha and Small Buddha, they were destroyed in the act. Okay. So terrestrial photogrammetry, utilization of terrestrial photogrammetry for documentation gained momentum from this project. Okay. Now, as you must be aware that early man, they used to draw some drawings on the stone, on the caves where they resided. So these are called as petrographs. And not only the monuments, these petroglyphs also can be documented, can be the 3D monument or 3D documentation can be done for these also. So this was done for Palpa area. In India also, we are also having a lot of petroglyphs. Petroglyphs are the drawings on the stones done by early man. As you can see here, this is a very this is some carving on the church or some monument. So 5 images were captured for this particular carving. And what I want to show you is that even in the photographs, the details are not very clear, whereas in the 3D model, the exact details are clear. Okay. Because in the 3D model, we also have the depth information. Okay. So such type of work can be very, very useful for restoration, for further work in monument area. A very small Buddha statue, just 50 centimeter by 30 centimeter, and was captured from the terrestrial photographs were captured. You can see the Buddha statue has been reconstructed. Okay, so these are some examples by which you can understand that how terrestrial photogrammetry can be used for creating 3D models. And these 3D models, now this 3D model is not the ultimate thing. This 3D model can be used for various other applications. a few of the applications we will be discussing in course of today's and tomorrow's lecture. Some of the case studies that we did at IIRS, I'm going to show you. These were all done. Okay, so sorry for that interruption. There was some technical issue. There was some lagging in the slideshow. So I will try to take care. And now these are the cultural heritage that were these studies were carried out at IIRS using terrestrial photogrammetry. So clock tower in Dehradun, Gillespie's monument, as you can see, every monument has been captured from multiple camera locations. Then the wireframe model can be generated for every monument. You can see wireframe model is generated. After that, shaded model is generated, and later on, the texture from the photograph is pasted here, and the photorealistic texture is generated. Now, this is another monument here in Dehradun, that is Buddha temple. So this is a very huge monument, and multiple photographs were captured for this monument. And as you can see here, the camera stations are given here. The shaded model and the point cloud, 3D point cloud is generated. After giving the texture to this texture model, I wanted to show you how much detailing can be done using terrestrial photogrammetry. So you can see the top kalash of the monument that is placed on the top of the lotus flower. That is also clear. The the petals of the lotus flower, even though this monument is very tall, very high, then also everything was clearly picked up by the 3D model. Another structure of heritage importance in Dehradun is Forest Research Institute, a very huge building which houses the Forest Research Institute. So a total of 56 photographs were captured throughout from all around that building, and this building was also the 3D model was generated. Okay, so these are certain studies to show you how terrestrial photogrammetry can be used for 3D model generation. This is the realistic reconstruction of IIRS campus. There are various buildings in IIRS campus. So multiple buildings were created, the trees were created. So you can see a complete reconstruction of the campus was carried out. So like this, and this was done using terrestrial photogrammetry, and very low instruments were used. Okay. These are different buildings within the IIRS campus. Now, to carry out the open source terrestrial photogrammetry, IIRS has come up with the open source application which is called as Thrivim. Thrivim utilizes only the camera or smartphones and generates the georeference 3D models. So the inputs that are required for Thrivim are overlapped sequence of photograph, location of camera, structure and footprint of building, and such sort of 3D models can be generated using Thrivim. Thrivim is an open source freeware application, and it is available at India IIRS site. So the output that is generated here is georeference 3D model, and the beauty of this georeference 3D model is that it contains the database also. So suppose in one building there are multiple floors are there, so you can slice the building into various floors and put the database accordingly. Or what you can do, within one floor different shops are there, different apartments are there, so you can put the database of individual apartments also. The database is can be the structure of database is can be done using the operator. Whoever wants to create whatever database, they can input that type of database. So someone can be interested in how many people are residing, what is the socio-economic condition of that of the people in that building, or someone can be interested in any other database. So this type of low-cost solution can be used for augmented reality, for spatial data infrastructure, for urban governance, for potential tax estimation, for property management. It can be also used by Department of Tourism, Ministry of Culture. For so many applications are there. Okay, now coming to the next technology, that is laser, LIDAR, light detection and ranging. So LIDAR is laser-based remote sensing technology. A small laser at a surface and measures the time it takes for the laser to return to its source. So what is done is, laser is an active sensor. Now there are two types of sensors. Passive sensors are the one which take the energy of the sun. Okay, which utilizes the energy of the sun. The active sensors are the one which give out their own energy. This energy is sent towards the object, towards the target. It strikes the target and it comes back to the sensor. The time of flight between the sending and receiving of this energy is noted down, and based on certain other parameters, the precise information about the target or terrain can be generated. The advantage of active remote sensing is that it can be done during day or night. It can compare the energy sent and energy received, so we can also know how much energy has been reflected, how much is absorbed, so we can know what is the type of target. And it makes mapping possible through the vegetation in low contrast situations or shadow areas. So as you must have been told in yesterday's session, that in highly vegetated areas, laser scanning can be done to know what lies beneath the canopy. Laser gives us a discrete data, and it provides the precise details of the scene. The complete vertical profile of the scene can be generated. It can also penetrate into water and a canopy. As you already know, that we can have multiple returns from the laser, or we can also have first return, last return, or a complete waveform from the laser data. Laser as a sensor can be put on any type of platform. You can put it on satellite, you can put on aerial, a drone, you can put it on moving vehicle, or you can put it on, make it as static laser scanner also. What we will be doing is using terrestrial laser scanner, the static one, for archaeological applications. So now coming to terrestrial laser scanner, the laser emitted from the scanner hits the object and is reflected back. So as you can see here in the figure, in the diagram, the laser scanner is emitting the laser. It strikes the object and it comes back and it is reflected back towards the sensor. Now the sensor catches this reflected energy. The time of flight is calculated, how much time has been taken in going and coming back of the laser, and XYZ coordinates are calculated using that. Terrestrial laser scanner is a non-contact surveying method of gathering thousands and thousands of points in few minutes. Using terrestrial laser scanner, entire region, both inside and outside the defined window, can be scanned in minutes. Also, the laser scanner gives us the accuracy of the points in centimeter and millimeters, in range of millimeters. This diagram shows what are the steps of laser data processing. The laser data processing and data acquisition, it starts with planning of the project. How? Because you have to plan properly from where you are going to place the laser scanner, what positions laser scanner would be placed, so as you can get the most efficient data acquisition from least number of laser positions. So once the data has to be collected using TLS, GPS, photographs, anything, then because one single monument or one single building would not be covered in one scan, so multiple scans would be required for covering one particular object. So to stitch these scans together, you require registration or georeferencing of scans from single campaign. Once you have done that, there would be certain noise elements also which have come, so such as any noise that you don't require, so you can do the editing and cleaning of that point cloud data. Once this point cloud is ready, you can export it into any type of format, and you can do any type of processing or any type of application using this particular point cloud. You can integrate it with other data sets. You can do photorealistic modeling. You can do surface modeling. You can do a combination of scan data from multiple companies for time series analysis, and so on. Okay, we will not. Once your data is collected, as you can see here, the terrestrial laser scanner data is something like this, in this black and white form. Okay, so later on you would like to incorporate the color or the texture from your photographs onto this point cloud. So for that, there is a camera that is put along with the terrestrial laser scanner, and using that photographs of that camera, the point cloud XYZ coordinates, or each point is given the RGB values, the red, green, and blue values, so that you feel that the point cloud is colored now. So these are the raw point cloud for some of the IIRS buildings. As you can see here, what I want to show you here is that the level of detail that can be taken from terrestrial laser scanner. So we have taken one scan, and from there was a porch in front of the building, a door was there, the glass door is there, and inside the door there is a veranda, and after that the stairs are there. So you can see, when I have zoomed, shown you a magnified view, even the stairs are so clearly visible. Similarly, in the second image, when we zoom it in an area, whether the window panes are open, closed, each and every detail is seen here. Okay, at this moment we have not incorporated the colors to the TLS scan. Okay, so now this terrestrial laser scanner can be used for digital documentation of cultural heritage site. So we have carried out certain studies, so I will be showing you. This is St. Mary's Church in Lansdowne area. It was constructed in the year 1895. Very old church is there. So data acquisition was carried out. The TLS scan was taken from outside as well as inside of the church. Once this TLS scan was done, you can see all the scans were co-registered and a complete 3D model of the church was generated. This 3D model was also provided color from the photograph. You can see the color is seen here. Now, for documentation and easy access, the point cloud was then unrolled so that the distortions are not there. The point cloud was also rasterized at different resolutions, as you can see here, 5 millimeter, 10 millimeter, 20 millimeter. This was all done so that, because the point cloud is very, very heavy, so many lakhs and lakhs of points, so the file becomes very heavy. So the display of the data becomes very difficult. And when we want to identify, when we want to apply any image processing application on this, supposed to find out where are the cracks in this building. Okay, so if we apply it on the highest possible resolution, it becomes very, very difficult for the computer to operate because the data is so heavy. So what we do is we do it on the lowest resolution. If we find something, then we go on simply. The display of the point cloud also becomes difficult when it is very heavy point cloud on the web environment. Now, the same Buddha temple that I have shown you, which we have done using terrestrial photogrammetry, the same one we have done using terrestrial laser scanner also. So you can see this is the Buddha statue. I have shown a magnified view of the stairs, and this is a Buddha temple and Buddha statue. This is a huge Buddha statue in the same complex, and we have kept the terrestrial laser scanner on the ground itself. Still, you can see even on the top of the statue, the head of the deity also is showing all the details. Each and every carving, everything is so clearly seen here. Similarly, for clock tower, the one I have shown you, using terrestrial photogrammetry, the same thing was done using terrestrial laser scanner also. Okay, so terrestrial laser scanner, as you must be observing, is able to give us very dense point cloud. Okay, but then again, terrestrial laser scanner is expensive, not available for everyone to use. Like we have created Trivim for terrestrial photogrammetry, we have come up with a new application for digital health assessment using range and optical data for heritage and archaeological restoration. How we can utilize this TLS point cloud for archaeological application. So this application is called as Dharohar, and it is basically done. It is basically developed for visualization of point cloud using terrestrial laser scanner. How, if we have two different point clouds, we can co-register it. Then all the entire methodology that we have developed in the for our application, we have brought this methodology here. So how the point cloud can be unrolled, how damages can be detected. So all that is done, can be done using this Dharohar application. And Dharohar stands for Digital Health Assessment using range and optical data for heritage and archaeological restoration. So prototype framework for damage detection using point clouds and multi-scale representation for assessment and reconstruction. Now, with that background work that we have done, IIRS has done one project on 3D digital documentation, damage assessment, and reconstruction of cultural heritage sites. What we have done is we have taken up UNESCO World Heritage Sites of Humayun's Tomb, Qutub Complex in Delhi area, and Nalanda Mahavihar in Bihar. These three sites were taken up for detailed analysis um, using the terrestrial laser scanner. And the study was focused on comprehensive 3D digital documentation, architectural primitive extraction, 3D digital blueprinting, damage detection and virtual reconstruction, and conjectural reconstruction. So 3D modeling is not the only thing that can be done using terrestrial laser scanner. Once this 3D model is generated, you can use that 3D model for variety of application which can be used for archaeological studies, and these are few of the applications that we have carried out. So I will show you the results of this. These are the study sites that we have taken up. This is Humayun's tomb in Delhi, Qutub complex again in Delhi, and within this Qutub complex, as you must be aware, there are multiple buildings are there, and we have done the 3D modeling of the entire complex area, 3D digital document of entire Qutub area, Nalanda Mahavihar, and Humayun's tomb has been done. In tomorrow's lecture, we will be showing you how this automatic 3D documentation and digital blueprinting of the monuments as well as damage detection was carried out using 3D point cloud generated through terrestrial laser scanner. Now, this is the final 3D point cloud using terrestrial laser scanner. This is for Qutub Minar, this is for Humayun's tomb, and for Nalanda Mahavihar. These are individual objects, individual monuments within the various complexes. So in the Qutub complex, these are the broken arches. As you must be aware, there are two sets of arches, one in front of iron pillar and one in front of Qutub Minar. So we have done certain other study also on these broken arches. So these are the 3D models, 3D point cloud collected using terrestrial laser scanner. Okay, these are the Qutub, within the Qutub complex. There are lot of pillars are there. Pillared gallery is there. So this is pillared pillar from that gallery. This is Alai Minar, which is an incomplete minar within the Qutub complex. This was also supposed to be similar to Qutub Minar, but was never completed. This is a tomb of Imam Zameen in the Qutub complex area, tomb of Iltutmish. These are Nalanda Mahavihar. Within that, there are various monasteries. So this is the 3D point cloud of Monastery 1. So there are various monasteries and various temples. So these 3D point cloud, we have placed 3D models have been placed on the satellite data, satellite derived NULC information. So for various areas, these are the textured point clouds. Okay, I will show you one virtual just, I'm really sorry that file is not opening. Now I will show you this video. Okay, so this is the point cloud of the entire Qutub complex area. Okay, now such type of point clouds can be used for virtual tourism also. Okay, virtual tourism in the sense these, suppose in this time, because of the current scenario, we are not able to move around, we are not able to go to other places. Okay, so such type of 3D documents or 3D models can be generated of for a particular area, and virtual tourism can be done. In this model, we have not done a lot of editing, and some blank areas you can see, but this is doable, it can be easily done. So this is, you can see, this is the Qutub Minar. You can move around. Also what you can do is you can add certain documentary also here. Okay, so, such as when it was created, and create a complete virtual look. Okay, so this was the pillared gallery that I was talking about. These are the pillars that I was talking about, the pillared gallery. In the coming slides, I will be telling you that how these, okay, that is Alai Minar, the incomplete Minar within the Qutub complex area. This is Alai Minar. Okay, now coming to the other part, Tomb of Iltutmish. There are various other buildings here. Okay, you can just walk around and do a commentary, and the entire thing can be, it can come up as a virtual tour. Okay, you can see the carving of on the top, the pillars, the carving on the pillars. This is the iron pillar which never rusts. These are the broken arches that I was talking about. Okay. Now, because the movement is so fast, that is why at some places you are feeling that the number of points are less, but the number of points are very high, and you can have the exact XY. The beauty is that you can have exact XYZ coordinates of each and every point here. For each and every point, XYZ coordinates. Now I will show you the detailing that can be obtained using the terrestrial laser scanner. You can see. You can see each and every carving is visible. Yeah. Okay. Like this, you can generate a virtual tour of the entire area. So what I will do is I will stop it here, and we will continue with our presentation, because I want to show you the other applications also. Okay, now since you have seen the virtual tour, what now this point cloud was used for various other applications also. Now, one of this application is conjectural reconstruction. Conjectural means we are assuming that this should have been like this. Okay, so now what we have done, we have seen that in the Qutub area, we have found these broken arches. Okay, they were not broken from always. At some point of time, they were when they were constructed, they were intact. So at that time, how they were. Okay, so how to see that? So what we have done is we have looked into the previous literature and got a very old map of that Qutub complex area. This map was is can be has been taken from a book which is the World Heritage Complex of Qutub, and this map was created in 1316. So in this 1316 map, the complete arches are seen here. I have shown it in with a red box. You can see here. So in 1316, these arches were complete. Now these are broken. So what we have done is we have geo-referenced this map, scaled this map, and scaled it with respect to our 3D model of today. Okay, and then what we have done is because this map has complete arches. So what we have done is, at what angle we have identified, we have calculated the angle, dimension and angular measurement of the complete arch were done using the georeferenced map. After that, we have established a mathematical relationship between these arches, the angular measurement of the arches and the angular measurements of our broken arches. A simile was a mathematical relationship was estimated, and finally the dimension and shape for reconstruction was done. So you can see here, this was conjecturally restored virtually only. So these are the broken arches. The black line depicts the broken arches that are standing at the Qutub complex in today's time. And and this red line is the conjecturally reconstructed based on the map of 1316. Once this was done in the form of the line diagram, a 3D model was also created. You can see a 3D model was created. And this 3D model was textured also, textured based on the texture of the today's pillar. And this is the actual ground scenario. You can see here. If any one of you have visited Qutub Minar, this is a very iconic photograph of Qutub Minar taken from in between these broken arches. So this is the actual ground scenario, and this should have been the scenario in 1316. This is conjectured scenario. Okay, so you can see how this, once we have this 3D model, this 3D model can be used for various applications. So this is one of the applications. Similar thing was again done, as I was showing you in the walkthrough model. I was showing you the pillared verandas were there, pillared galleries were there. So the same map was used for reconstruction of this pillared gallery. You can see the gallery was in 1316. The entire area was having this type of gallery. Okay, now only a small portion is remaining. So what we did is, conjecturally we have restored the entire this pillared gallery. Okay, so this entire area has been conjecturally reconstructed, and you can see here, this is the zoomed in version of a part of the pillared in gallery, from which I have shown you in the walkthrough also, and this is the when we put texture also on it. Now, another thing that we have done in our studies was estimation of tilt of Qutub Minar. And this all was done using TLS point cloud. So TLS point cloud was taken as the base for all these studies. So what we have done is, because ASI, they reported that Qutub Minar is getting tilted in the southwest direction. So what we did was, we have this entire point cloud of the complete Qutub Minar. So what we did, and you must be knowing that this Qutub Minar has various stories. Okay, 1, 2, 3, 4, and then top is there. Okay, so what we did was we have visualized the point cloud from the top. You can see this is the top. The top point was taken, and we have marked the circle for every story, because at every story there is a gallery. Okay, so we have made that, done certain calculations, and what we found is that the certain amount of tilting is there. We have identified the plumb line of straight minar and plumb line of tilted minar, how much angle of tilt is there, and then we correlated it with the ASI document. ASI document was carried out in the year 1964. They have done the calculation, and I think in the year 80s or something, they have done certain restoration work. So after that restoration work in the southwest direction, after that the tilting has stopped. Now it is no more tilting, but till that time, till there was some channel of Yamuna flowing from below, something was there because of which it was tilting. So we have done all the calculations and correlated it with the ASI measurements. So ASI measurements were done on the ground. We have done the measurements on the point cloud. So this is the advantage of having the point cloud. Now, another application is virtual relocation of the statues. Now, this was done in the Nalanda Mahavihar area. So, as you must be aware, that Nalanda Mahavihar was a university in which there were certain temples, there were certain monasteries, and in the monasteries, the students used to stay. There were rooms in the monasteries for the students, lodging was there, and in the temples, while the excavation was done, a lot of statues were also excavated. Okay, but these statues were taken out from their position and they were kept in the museum, so that they are protected from the weather and from some other calamity. So now, but for these statues, the exact position from where they have been excavated is known to us. So what we did was, we have created the 3D model of the temple. Okay, this is the 3D model of the temple. We went to the museum, and in the museum, we have taken the 3D model of these statues also. Now, two virtual things, we have placed the statue exactly on the position from which it was excavated. This we have done for various statues in the Nalanda Mahavihar area. Now, once we have placed these statues, and once now we create a walkthrough model, so it will appear that the statues are sitting there, and at the time of excavation, how they were looking. So you can see here, these for all these Nagaraj statue, for standing Buddha, for Bodhisattva statue, for all of them, we have done the relocation, virtual relocation of these statues. So this is another application that can be done. We can also generate 3D model of various artifacts that are available, that are present after the excavation in the museum. So these are some of the artifacts which we have taken from the museum. So this is the Nalanda seal. When the excavation was carried out, after many years, the archaeologists were able to say that this is Nalanda site. When the seal of the university was found at that site, then only they were able to confirm that this site is Nalanda University. Okay, these are the vessels. Huge vessels are there, because as I already told you, in the monastery, the students used to stay. So these are the cooking vessels which were found from the monasteries. Okay, so the relocation, virtual relocation of all these statues, all these artifacts was done virtually using the 3D model. So these are few of the applications which can be done using, once we have the 3D model. So these are just some of ones that I have shown you. There can be others also. We will be two of them we will be discussing tomorrow. especially on the damage detection, how to know how much damage is happening, estimating the damage, the cracks, and all those, identification of cracks. And the second one is, as I have already told, the complete digital documentation, blueprinting of the monument. Okay, so today I have told you how to generate 3D model, how to generate virtual tour of the model, and some other applications of these 3D models. The main application of the 3D model, that is the digital blueprinting, we will be discussing tomorrow. So thank you all for attending this session. You can post your questions. We will be taking up your questions in just while from now. Thank you so much.